Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, in this course, I will deliver my lecture on regional metamorphism of basic or mafic rocks. I will cover this topic in two parts. In part 1, I will cover under the following heads: regional metamorphism, introduction, Barrovian facies series, geolite facies and mineral assemblages. Hope it will be useful for you. Try to be regular in course. Regional metamorphism is metamorphism that occur over broad area. Most regionally metamorphosed rocks occur in area that have undergone deformation during an orogenic events, resulting in mountain belts that later have been eroded to expose the metamorphic rock. On the basis of the pressure and temperature, we can divide the metamorphic phases into three types, mainly phases of low pressure, B phases of intermediate pressure, and C phases of high pressure. Maya Siro originally recognized three different phases series. First, a geolite, prehenite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized by green schist, epidote amphibolite, gaulite type characterized by paragenesis of kyanite, selemonite type. And third, an Abukama type of green schist, amphibolite, gaulite characterized by paragenesis of andalusite, selemonite type. Regional or Barrovian metamorphism cover large area of continental crust typically associated with mountain range, particularly subduction zone or the roots of the previous eroded mountains. The regional metamorphosed rocks occur during an orogenic events. The collision of two continental plates of the Iceland arc with continental plates produce the extreme compressional forces required for the metamorphic changes typical of regional metamorphism. The phases of intermediate pressure or Barrovian type. The basalt and andesites are important basic or mafic rocks. The important constituents of basalt is calcic plagioclase, anorthite 40 to 70%, and clinopyroxene augite with hypersthene and olivine. The bulk composition is defined in terms of main components CaO, Na2O, Al2O3, MgO, FeO and SiO2. Basalt constitute a major portion of oceanic crust and are also widespread in geosynclines in form of lava flow, dike and sill. The important minerals assemblages and reaction in the mafic rocks can be observed by ACF diagram of Ascola. Metamorphism of basic or mafic rocks is important because of their mineralogy on the basis of metamorphic phases and give idea of tectono-metamorphic evolution of a terrain. The pre-existing chemical composition, initial composition of the rock is responsible for the mineralogy of its metamorphic offspring. When we normally study the metamorphic rocks, it is essential to keep in mind about the parental composition of the rock. In fact, the chemical composition of the rock protolith can only provide the important clue towards deducing the parents. We can keep certain sedimentary and igneous rocks into 6 important compositional based group. First, ultramafic rocks, mantle rocks, cometite and cumulates, very high Mg, Fe, nickel and chromium. Second, mafic rocks, basalt, gabbro and some gravax, high Fe, Mg and calcium. Number 3, cells or peltic rocks, the most common sediments, fine grained clastic clay and silt deposited in a stable platform or offshore weighs high Al, potassium and silica. Fourth, carbonates or calcareous rocks, mostly sedimentary limestone and dolomites or dolostone, high calcium, magnesium and CO2. Fifth, quartz rock, chert or arsenic and sands are moderately high energy continental clastic, nearly pure SiO2. Sixth, quartzo-feldspathic rock, arkose or granitoids and rhyolite rocks, high silica, sodium, potassium and alumina. Although these 6 categories are to a degree of gradational and they cannot include the full range of possible parental rocks, but they do cover most type. High are responsible for metamorphic respective amphibolite, a metamorphic rocks dominated by hornblende and plagioclase. Amphibolites may be foliated or non-foliated. The protolith is either a mafic igneous rocks or gravax. Our scholar define metamorphic phases on the basis of metamorphosed mafic rocks and called metabasites. The regional or prograde metamorphic of mafic or basic rocks from the parent's composition to different stages, from geolite phases to eclogite phases. In contact metamorphism, basalt rock are recrystallized to mafic hornfels. The metamorphosed mafic rocks are called metabasic or metabasites. The rocks show the following sequence with increasing grade: first geolite phases, second greensice phases, third amphibolite phases, fourth gaunlite phases. The principal minerals changes in metabasalt are due to the breakdown of the two most common basalt minerals, plagioclase and clinopyroxene. As temperature is lowered, the more calcic rich plagioclase, the high temperature igneous plagioclase in the albite anorthite system become progressively unstable. The low metamorphic grade only albite anorthite 0 to 7% is stable. In the upper greensice phases, oligoclase anorthite 7 to 17% becomes stable. The anorthite content of plagioclase thus change from anorthite 0.7 to anorthite 7 to 17 as the grade of metamorphism increase, and is seen and more calcic plagioclase become stable in the upper amphibolite and gaunlite phases. Clinopyroxene break down to number of mafic minerals. These includes chlorite, actinolite, hornblende, epidote and a metamorphic pyroxene etc. are commonly diagnostic of the grade and phases. For the regional metamorphism of mafic or basic rocks, we have to compare all the phases of intermediate pressure, that is from geolite to gaunlite phases, in view of the major changes in mafic or basic rocks only during metamorphism. Very low grade metabasites are usually partially altered to a very fine grained rocks prior to the work of Clombs and co-worker in New Zealand. Such rocks were written off as altered and did not receive much importance from the petrologist. In New Zealand, during geolite phases of metamorphism, volcanic glass is altered to the geolite hollandite along with clay minerals like kaolinite, montmorillonite plus secondary quartz and carbonates. All transformation as a result of alteration primary mineral of pyroxene and plagioclase. The reactions are: plagioclase plus water give rise to analcine plus hollandite reaction number 1. Second, Augite plus water plus CO2 give rise to chlorite plus calcite, reaction number 2. This is the initial stage of metamorphism, very low grade, characterized by a geolite minerals and therefore called geolite phases. The important mafic assemblages during geolite phases metamorphism with the help of ACF diagram. First, chlorite plus hollandite or lomentite plus quartz plus minus albite. With increasing pressure and temperature, hollandite and stabilite change to other geolite minerals. Hollandite give rise to lomentite plus quartz plus water, reaction number 3. Lomentite can also form by breakdown of anorthite. Anorthite plus water give rise to lomentite, reaction number 4. Veracite is formed by the reaction lomentite give rise to veracite plus water, reaction number 5. Albite is formed by the reaction analcine plus quartz give rise to albite, reaction number 6. The reaction 3 to 6 occur at 200 to 300 degrees centigrade between 1 to 3 kilobar, denoting upper temperature range of geolite phases. Further increase of pressure temperature, the geolite phases move towards prehenite pumpelite phases and actinolite. During this change, we can observe the following assemblages: chlorite, prehenite, calcite, and third, pumpelite plus actinolite plus chlorite in upper part, higher grade. Similar alteration is reported in the Greywax volcanogenic sandstones. Since the hydration of igneous assemblages is never complete due largely to the non-pervasive penetration of sea floor basalt by seawater, hollandite and lomentite are equally abundant in ocean floor. Hydrothermal metamorphism revealed from degrading of samples from MOR and also in burial metamorphism of mafic seals. At higher temperature more than 200 degrees centigrade, the geolite in the metabasites are replaced by prehenite Ca2, Al2, Si3, 10 OH twice, pumpelite Ca4 under bracket MgFe bracket close under bracket AlFe bracket close 5 Si6 O23 OH thrice 2S2O, actinolite Ca2 MgFe5 Si8 O22 OH twice, and epidote Ca2 Fe Al2 Si3 O12 OH. According to the reaction, lomentite plus calcite give rise to prehenite plus SiO2 plus CO2, reaction number 7. Another reaction is lomentite plus prehenite plus chlorite give rise to pumpelite plus quartz plus water, reaction number 8. The actinolite formed by the reaction pyroxene plus water plus CO2 give rise to actinolite plus quartz plus calcite. Further increase of pressure and temperature, the pumpelite disappear as the rock enter the greenschist phases where it first replaced by the actinolite and epidote. The important reaction Fe chloride plus calcite plus oxides give rise to actinolite, reaction number 9. Lomentite plus actinolite give rise to prehenite plus chlorite plus quartz plus water, reaction number 10. Another reaction lomentite plus actinolite give rise to pumpelite plus chlorite plus quartz plus water, reaction number 11. The assemblies prehenite, pumpelite, epidote with albite, chlorite and some carbonates belong to the prehenite pumpelite zone or phases reported from subduction zone metamorphism. Lomentite unstable at higher pressure. The reaction is lomentite give rise to lawsonite plus quartz plus water, reaction number 12. Lawsonite plus quartz give rise to geosite, epidote plus pumpelite plus water, reaction number 13. The greenschist or greenstone start when the mineral prehenite and pumpelite disappear and green minerals such as actinolite, epidote, chlorite appear. Prehenite give rise to geosite, epidote plus grassolarite plus quartz plus water. Reaction number 14 occur at 350 degrees centigrade 3 kilobar. Another reaction is pumpelite give rise to geosite plus prehenite plus chlorite. Reaction number 15. The Green's phases includes the common products of low-grade regional and dislocation metamorphism. The metamorphism of mafic rocks is first evident in the Green's phases, which correlate with chlorite, biotite and almandine zone of these associated peltic rocks. Although relicts igneous textures may be preserved, the mineralogy reflects re-equilibrates to metamorphic condition. Green's phases are characterized by the abundance of green color minerals, for example, chlorite, epidote, actinolite, and quartz. The association of albite and anorthite less than 7 and epidote is characteristic of these phases. Furthermore, chlorite in presence of quartz and muscovite. Other diagnostic minerals are mica, muscovite and biotite, microcline, pyrophyllite, kyanite, garnet and hornblende, etc. We can observe the following basic assemblages with the help of ACF diagram: albite, anorthite less than 7% plus epidote, chlorite, actinolite, tremolite plus minus quartz. Mafic or basic assemblages in biotite zone. There is no major change in basic assemblages during biotite zone of Green's phases. The basic assemblage is same as in chlorite zone except the appearance of biotite. Biotite, albite, epidote, chlorite, tremolite, actinolite plus minus quartz. During almandine zone of Green's phases, almandine rich garnet and hornblende appear for the first time by the reaction FeMg chlorite plus quartz give rise to almandine plus Mg chlorite plus water. Reaction number 16. Another reaction is epidote plus quartz give rise to anorthite plus water. Reaction number 17. Chlorite plus actinolite plus epidote give rise to hornblende plus water. Reaction number 18. We can observe the following mafic or basic assemblages with the help of ACF diagram: hornblende plus epidote plus albite plus minus quartz. Second, hornblende plus epidote plus almandine plus minus albite plus minus quartz. In the higher pressure of Barrovian zone, hornblende appears before oligoclase as a transitional albite epidote hornblende phases proposed by different workers including Ascola may be useful in higher pressure temperature terrain, in low pressure temperature terrain and in contact areoles. The plagioclase transition occurred first. Metabasite in the amphibolite phases are characterized by the assemblage hornblende, plagioclase, anorthite more than 17% with less amount of quartz, epidote, garnet, clinopyroxene and biotite. Epidote usually disappears in upper amphibolite phases, that is stolite, kyanite, sillimanite, orthoclase zone in associated peltic rocks. In the ACF diagram, we can observe different mafic or basic assemblages during this phases of metamorphism, right from stolite zone, kyanite almandine zone, sillimanite muscovite zone and sillimanite orthoclase zone. Mafic or basic assemblages during stolite zone: hornblende plus plagioclase plus almandine plus minus epidote plus minus quartz plus minus biotite. Second, hornblende plus plagioclase plus minus epidote plus minus quartz plus minus biotite. Third, hornblende plus diopside plus plagioclase plus minus epidote plus minus quartz and plus minus biotite. The derivative of mafic or basic rocks in amphibolite, many of them are garnetiferous. Coexistence of Plesioclase anorthite 25 to anorthite 45 with epidote is common in these rocks. Important reaction: tremolite plus calcite plus quartz give rise to diopside plus CO2 plus H2O. Another reaction is tremolite plus calcite plus quartz give rise to hornblende plus anthophyllite plus water. There is no basic major change in assemblages of mafic or basic rocks. Changes during metamorphism of other zone of amphibolite phases, that is kyanite almandine zone, sillimanite muscovite zone and sillimanite orthoclase zone. The gammalite phases is characterized by the presence of large anhydrous mineral assemblages in metabasites. The important mineral assemblages is orthopyroxene, clinopyroxene, plesioclase plus minus quartz. Garnet is also common and minor hornblende and or biotite may be present. Hornblende may remain stable in metabasite in lower gammalite phases but dehydrates in the upper gammalite phases. The texture is generally gneissic and grains shapes are granular, thus resembles to the original basalt. The origin of gammalite phases rock is complex gammalite present unusually hot condition. They represent temperature excess of 700 degrees centigrade. Important reaction: a number of metamorphic reactions have been suggested to count for the diagnostic appearance of orthopyroxene. Anthophyllite give rise to orthopyroxene plus quartz plus water. Hornblende plus quartz give rise to orthopyroxene plus clinopyroxene plus plesioclase plus water, reaction number 19. Another reaction is hornblende plus almandine plus quartz give rise to orthopyroxene plus plesioclase plus water. Thus, disappearance of hornblende and anthophyllite marks the beginning of gammalite phases. Mafic or basic assemblages during gammalite phases. The important assemblages we can observe with the help of ACF diagram is as follows. Number 1, hypersthene plus plesioclase plus minus quartz, anderbite. Second, hypersthene plus plesioclase plus garnet plus minus quartz plus minus orthoclase, anderbite or basic charnockite. Third, hypersthene plus clinopyroxene plus plesioclase plus minus quartz, 2 pyroxene gammallites. Fourth, clinopyroxene plus plesioclase plus minus quartz. When subduction of the theolitic basalt morph is subjected to high pressure and low temperature environment along convergent plate margin, sodium rich amphibolite known as glaucophene is formed along with jadeite pyroxene, lawsonite and aragonite. Due to this assemblage, the rock is known as blue schist. The important reaction: albite plus chlorite plus actinolite give rise to glaucophene plus plesioclase plus water, reaction number 20. When subduction is fact, blue schist are often associated with eclogite. This happens at P and T are more than 14 kilobars and temperature of 800 to 900 degrees centigrade, where basic gammallites are transferred into eclogites. The rocks contain omphacite and pyrope with or without kyanite or anesthite and devoid of plesioclase. The plesioclase decomposes. Anorthite give rise to gracilorite plus kyanite plus quartz, reaction number 21. Jadeite component in the clinopyroxene is derived from the breakdown of albite molecules of the plesioclase of the basic gammallites. Albite give rise to jadeite plus quartz, reaction number 22. The different mineral reaction in basaltic rocks from starting to end of regional metamorphism, including eclogites. Formation are shown in a PT diagram. Dear student, today in this lecture, we have discussed about the regional metamorphism of basic or mafic rocks part 2. I have covered this topic under the following heads: green schist phases, amphibolite phases, ganoloite phases, blue schist phases, and eclogite phases. Regional metamorphism of mafic or basic rocks begin with the introduction, followed by the type of protolith, characteristic minerals, metamorphism of mafic or basic rocks, comparison from geolite to ganoloite and eclogite phases with the help of ACF diagram, important reaction, and on the basis of detailed study of different subphases along with the support of experimental data, we can conclude that during prograde metamorphism of mafic rocks, metabasites, amphibolites, and 2-pyroxene basic ganoloites are formed. I believe this lecture was useful for you.